Welcome to Manorama Horizon. My name is Thomas Thomas, and today we are here to consider a seemingly simple but very important and fundamental question in physics and mechanics. And the question is, when does work happen? When I was first trying to understand the concept of work and energy, I came across several scenarios where the textbook said that no work was being done, and I was very confused. For example, the textbook said that if I was pushing against a wall and the wall wasn't moving, no work is being done. But in real life, if I were to actually try something like that, I would become tired, right? I would be spending energy and I would become tired. So why was the textbook telling me that no work is being done? The confusion began to increase with each subsequent class because I would come across more scenarios where even objects which were moving were not performing work, and objects which were stationary may have work being done on them. So I would like to explore certain scenarios today, certain cases from the real world, and understand how we decide whether work is being done in a particular case or not. In physics, we have the idea or the concept of a system. What is a system? You can think of a system as a collection of interacting components. For example, if a child is hitting a football with his foot, the child and the football constitute a system, and this system has two components, the child and the ball. If a planet is revolving around a star, we can say that this is a system which contains two components, the sun or the star and the planet. The concept of system is central to understanding whether work is being done or not in physics, and we will understand this in some detail as we go through each of these scenarios one by one. So let us consider the first case and analyze the system and determine whether work is being done or not. So, is work being done when a planet is revolving around a star? Let's analyze the statement. So here we have a star. Let's keep things simple. This is our sun. It's been shining for millions of years, billions of years. And here is Earth. And Earth is very happy in this particular case. And the Earth has been going round and round the sun for a long time. The Earth has been in orbit around the sun for at least 5 billion years. The sun and the Earth are exerting forces on each other, the gravitational force. So we can say that there is a force which is linking their centers together, and that force is gravity. The Earth is clearly moving in a path around the sun. So here we have the two requirements for work to happen. We have a force being exerted on the Earth, and we have the Earth moving. So does this mean that work is being done when the Earth is moving around the sun? And the answer surprisingly is no. No work is being done when the Earth is moving around the sun. Now, what is the reason for this rather confusing answer? Let us consider the energy of this system, right? So, the energy of the system can be divided into two components. Due to the distance between the Earth and the sun, let's call this distance R. The Earth will have some kind of potential energy, right? If you have an object at a distance from another object and there is a gravitational force between them, those objects will have a gravitational potential energy. So the Earth has gravitational potential energy due to the distance it is maintaining from the sun. What other energies does the Earth have? Well, the Earth is moving. If you were to look at the Earth at any instant of time, the Earth definitely has a velocity. So the Earth has a tangential velocity v. And the Earth also has a mass m. And we know that in physics, in mechanics, if any object with mass is moving with respect to us, then it has kinetic energy. So, the Earth has gravitational potential energy or GPE due to the distance it is maintaining from the Sun. And in addition to that, it also has kinetic energy or KE due to the fact that it is moving. And the total energy of the Earth in this particular system can be considered the sum of the gravitational potential energy and the kinetic energy. Now, if we analyze the system carefully, as the Earth is moving around the Sun, we will make the simplifying assumption that it is a perfectly circular path. So, the Earth is moving around the Sun in a perfectly circular path. This is not really true, but it is close enough that we can approximate safely. In that particular case, if we look at this system from the top, so here we have the Sun and here we have the Earth, we notice that at any given point in this orbit, the sum of gravitational potential energy and kinetic energy remain the same. The sum of these energies will not change because the distance from the Sun is not changing and the tangential velocity of the Earth is also not changing, which means that the sum of GPE and KE is not changing. And a system or a part of a system is performing work only if its energy changes. Since there is no change in the energy of the system, no work is being done, even though the Earth is clearly moving under the influence of a force. So, we have to think deeply about the question of whether work is being done before we can make a judgment. No matter how simple the system may seem to us, there are these complications that we need to keep in mind. Now, we have another scenario. Is work being done when a fidget spinner is spinning at high speed? This little contraption is called a fidget spinner. And it has helped a lot of people, young and old, waste hour upon hour doing this. Now, I have to admit there is something incredibly addictive about this simple device. You could practically watch it going round and round forever. But it did raise an interesting question for me. How do we decide whether this device is doing work? Now, if this device is stationary, I clearly have to apply a force in order to get it moving. So I am applying a force causing an object with mass to go through some displacement. So clearly, if this object was stationary, if it was not spinning, I would have to perform some work to get it to move. What happens once it starts moving? It took some amount of work to get the fidget spinner to move. And the beauty of this device is that there is very, very low friction in its bearings, which is why it is able to keep spinning for a long time without any noticeable change in speed. Whether this object currently has energy and whether this object is currently doing work are two very different questions. And we are going to analyze this system based on what we have learned to decide whether the fidget spinner is actually doing work. For simplicity, we will assume that there is no friction. So, we just saw the fidget spinner spinning at high speed. So, it is moving at high speed. So, clearly, these bearings have a mass and clearly they are rotating at high speed, which means that each part of the system has a velocity, has a tangential velocity. And clearly there is a lot of energy in the system because the spinner is moving at very high speed. For the purpose of this discussion, we will assume that there is no friction in this system. There is no friction in this system, and the fidget spinner is being kept at a constant height above the ground. So there is no change in its gravitational potential energy, right? So there is no friction in the system, the fidget spinner is spinning very freely, and there is no change in its gravitational potential energy. We are not interested in how this fidget spinner began to spin. When we began our observations, the spinner was already spinning, and in the absence of any other forces, in the absence of any friction, the spinner will keep spinning at that speed basically forever. So the energy of this mechanical system, the spinner, can again be considered a sum of its kinetic and potential energy. If we consider the height of the spinner above the ground to be h, let's say that here is the spinner and here is your teacher holding it, and the height of the spinner above the ground is h. The gravitational potential energy for this spinner can be given by the formula mgh, where m is the total mass of the spinner. So this is mass of the spinner. H is the height of the spinner above the ground, and g is acceleration due to gravity. So this is one of the energies possessed by the spinner. What other energy does it have? It is spinning at high speed, the components are moving at high speed, so it also has kinetic energy. More specifically, it has rotational kinetic energy, which you will learn in detail in higher classes. So this is not the kinetic energy of an object moving in a straight line. This is rotational kinetic energy. In this particular case, we have assumed no friction, and we already know by Newton's second law that if the object is not changing its momentum, right? If there is no change in the speed of this object, there is no change in the momentum of this object, then no force is being applied. There is no external force being applied on this object. From the first law, we also know that if the object is already moving, or if it is already rotating, it will keep rotating at that same rate forever. It will neither decrease its speed of spinning, it will not increase its speed of spinning, which means that the kinetic energy of this system, the rotational kinetic energy of the system, is constant. This energy is constant, it is unchanging with time because the spinner is not speeding up, it is not slowing down, and if we keep it at constant height, the GPE is also constant, which means that the sum of these two energies will also remain constant. In other words, the energy of the system, that is the fidget spinner, is not changing with time. It is neither gaining energy, it is also not losing energy. So even though, again, the spinner is clearly moving, it has energy, it is not performing any work because there is no change in the state of energy of this system, whether it is kinetic or whether it is potential. Next scenario. Is work being done when we hold a heavy object in our hands? When I was little, one of the punishments that my PT instructor would give us is for us to hold a moderately heavy brick in our hands. So we would have to hold a brick like this, and it would not take us much time before we started to sweat profusely. So you can understand why I felt very angry and betrayed when I read in the physics textbook that I was not performing any work, even though I was clearly getting tired of this activity. So why do we say that we are not performing any work in this case? Once again, we have to first decide what constitutes our system. If this object, this brick, constitutes our system, what energy does it have? It is not moving with respect to me, clearly, so its velocity is equal to 0. Since kinetic energy is equal to half mv square, if velocity is 0, this implies that kinetic energy is also 0. So this brick or this object has no kinetic energy in this scenario. Does it have potential energy? It is situated at a height above the ground. Let's call this h. It definitely has a mass, which I can feel clearly. As a result, it also has weight because this mass is under the action of a gravitational acceleration. So the potential energy of this brick, our system is the brick in this case, the gravitational potential energy again is equal to m times g times h. And if I am able to hold this brick at this constant height under the influence of this gravitational force, it will mean that the brick has energy due to its position. So it has potential energy. However, I am not raising the brick, I am not lowering the brick, which means that there is no change in the gravitational potential energy. In physics, we use the Greek letter delta. So this is delta in order to represent change. So in this case, again, delta GPE is equal to 0, which means once again, despite our immense sadness, no work is being done in this system. At least we can say accurately that no work is being done on this brick because its energy state is not changing. You could reformulate this question: is work done when I am lifting this brick from the ground towards this height? In that case, yes, work was done when I lifted this object, because in that case, the displacement of the object is clearly changing. At ground level, h is equal to 0. So at ground level, mgh will be equal to 0. So there will be a change in the energy level of the system by the fraction mgh minus 0 equal to mgh. So if I were lifting this brick above the ground, I am performing work on the brick. But if I am just holding the brick in position, at that time I am not performing any work because I am not changing the energy level of this system. Another scenario: is work being done when an object is being pushed along in space? Right. So let us imagine that you are an astronaut. And you have a Rubik cube in your hand for some reason. So here is our Rubik cube. And you are applying a force on this object. So you have applied a force on this object, force F. And as a result, the Rubik cube has started to move. So here is the Rubik cube. And let's say I'm the astronaut. So I apply a force on the Rubik cube, and as a result, it starts to move. Now we are in outer space. So once again, we can safely make some assumptions. So one assumption is that there is no friction. Outer space is a vacuum. There are no air molecules which can cause friction with this object. So there is no friction. And as a result of the force we have applied, this object will accelerate. It will acquire certain velocity. And as a result, it will start moving through space and will have a displacement dependent on time. The longer the time it takes for the object in that velocity, at that velocity, the larger the displacement, the greater the displacement of the object. Now, this presents a problem. At least it was a problem for me when I was studying this concept, because in space there is no friction, and in the absence of friction, this object will keep moving. This Rubik cube will keep moving at constant velocity, which means that the displacement covered by this Rubik cube depends only on time, right? So if it is, let's say it is traveling at 1 meter per second. So in 1 second, it will travel 1 meter. In 10 seconds, it will travel 10 meters. In a million seconds, it will travel 1,000,000 meters. So when we are going to use the formula, work done is equal to force multiplied by displacement, which of these values should I use? Because if I wait for an infinite amount of time, this Rubik cube will travel an infinite distance, which would imply that an infinite amount of work was done, which makes no sense because I do not have infinite energy. So clearly something was wrong with my assumptions. I was making some kind of a conceptual mistake when trying to decide how much work was done. And the mistake is this: we can calculate work only when the object is moving through a particular displacement under the influence of a force. So when I applied a push on this object, the moment I lose contact with the Rubik cube, the force applied becomes zero. So when I am calculating the work done on this object, I can only look at the displacement covered by the object when it was still in contact with my hand, when it was still under the influence of a force. And that amount of displacement and that amount of work will always be finite. So when was work happening? Work was happening when I applied a physical force on the Rubik cube, and the moment I lost contact with this Rubik cube, it began to move through space at a finite velocity, in which case it has a definite amount of energy. It has a kinetic energy. We will assume that we are not near any planets or stars, so we can consider the gravitational potential energy to be zero. So it has energy, but it is not performing any more work, because as it moves through space, it is moving at constant velocity now. So it is not performing any work. At the time when the force was being applied on the object, it was accelerating. It was moving through a particular displacement under the influence of a force. So we will only consider that time, that interval when a force was being applied on the object to enter the value of displacement. So this is how we resolved the paradox of how can an object move an infinite distance even though its energy is finite. So here's another scenario. Is work being done when an object is being pushed along a surface? In physics, when we are considering the questions of forces applied and work done, it is important to remember that we can classify forces into two broad categories, and these are conservative forces and non-conservative forces, and the difference between them is how they respond to the question of work being done in a system. Consider this Rubik cube. If I were to want to move this cube on this surface, I would have to apply a force. So if I apply a force, the Rubik cube moves. And if I apply a larger force, the Rubik cube moves a little farther, but it always comes to a stop. If I had done this experiment in free space and if I had applied a force, in the absence of any other forces, the Rubik cube would have accelerated to some velocity and kept on moving at that velocity forever. But that is not what is happening here. I place this object on the surface, and if I apply a force, it moves for some distance and then stops. So the question arises, what is the difference between these two scenarios? Further, let's consider one more example. This is a spring-driven car. It contains a small spring inside its mechanism, and when we force this car in the direction of the spring getting compressed and release it, the car starts moving. So what we did here is, we were applying a force against the tension in the spring. So we performed some work. But when we released the car started moving in the opposite direction. So whatever work we did in order to wind up the spring was recovered when we let the car go. So again, I perform some work to wind up the spring, and when I release the vehicle, it starts going on its merry way. The same thing is not happening with this cube. If I were to pull this cube back, clearly I'm applying a force, clearly the cube is moving in response to the force, work is being done. But the moment I release my hand, nothing happens. The cube stays exactly where it is. So what is the difference between dragging this cube across this table and moving this vehicle across this table? What is the difference between the forces involved? Well, the forces involved with this cube are frictional forces, and frictional forces are non-conservative. And the reason they are non-conservative is the work that you do against them cannot be recovered. Please note, conservation of energy is valid in every single case. It is not as if we are violating the law of conservation of energy. The difference is that whatever mechanical work I performed in dragging this object was turned into the movement of this object and turned into waste heat due to the friction between this cube and the table. And this energy is not recoverable. Dragging this object across the table does not store any energy in this object. The work that I am performing is not being stored in this cube. On the other hand, if I were to lift this cube into the air, I am applying a force against the force of gravity, and the work that I have done in lifting this cube is now stored in the cube as gravitational potential energy, which I realized the moment I dropped the cube. The energy that I had stored in this object in raising it against gravitational force gets turned back into kinetic energy as this object drops back down, which is not what happens when you move this object against the force of friction, because gravity is a conservative force and friction is a non-conservative force. The same thing happens with this car. If I drag this car backward, I am acting against the force of the spring. The elastic potential of the spring is being increased because whatever effort I make in moving this car backwards, the work done is being stored inside the elastic potential energy of a spring. And that is a conservative force, because the moment I release the car, the energy is turned back into kinetic energy. The energy stored in the spring gets turned back into kinetic energy. So always pay attention to whether the forces that you are acting against are conservative forces or non-conservative forces. So one of the reasons students get confused by work and energy is because we are at a certain level imagining them to be the same thing. They have the exact same units, they have the exact same dimensions, but they are not the same thing. And here is a simple analogy to help you understand why they are not the same. Just as the amount of money in your bank account and your income and expenses are all measured in rupees or dollars or euros or Deutschmarks, whatever, right? So I have a given amount of money in my bank account that is also measured in rupees. I have some expenses that I have to pay every month. I have to pay my rent, I have to pay money for food, for electricity. Those are my expenses. And I also get a salary from my job, so that is my income. All of these things are measured with the exact same unit. But I would not make the mistake of thinking that my income is my expense or my expense is the bank balance that I have in my account. In the same way, work and energy have the exact same units. They have the exact same dimensions. They even have the same formulae. But work and energy are not the same thing. Work is the label that we put for a system whose energy is changing. So let us summarize what we have learned so far. In physics, work happens on a system if there is a change in its energy state. So what is a system? It is a collection of components, in this case objects, which are interacting with each other. Now, for a mechanical system, that change may be in the system's kinetic or potential energy. In mechanics, we are currently learning two concepts: the energy that an object has because of its position. That can be the energy of an object sitting above the ground, that is potential energy, or gravitational potential energy. If you have a rubber band and you stretch it, you are performing work to change its shape, and that is what we call elastic potential energy. And we also have kinetic energy, which is the energy of motion. So the energy of an object which is moving in a straight line, or moving in a curve, or rotating in place. All of these are various examples of kinetic energy or energy due to motion. If an object is moved by the application of a conservative force, the change in the system's energy is reversible. For example, if you apply a force on a spring, the amount of work you are doing in increasing the size or the length of that spring is being stored in the spring itself. So the moment you release the spring, it will go back to its original shape. You will recover the energy that you have expended in the form of kinetic energy. The same thing with gravity. If you perform work to lift an object off the ground and release that object, you will recover that energy in the form of kinetic energy when the object falls back towards the ground. So these are cases where you are working against a conservative force. For example, spring force or gravitation. If an object is moved against a non-conservative force, the work done is expended as waste heat and cannot be recovered. The most common example of a non-conservative force is simply friction. When you are pushing a heavy load across the floor, and if you suddenly stop, the load will also stop right there. It has no change in its energy because you have performed work against a non-conservative force. So no energy is stored in that object. It is simply converted into waste heat in the floor due to friction. So a system where you have friction, it can be a car driving on a road, it can be an object moving through the air. The energy being expended in overcoming the frictional force cannot be recovered. It will simply turn into waste heat and it cannot be recovered. So I hope that today's class has given you some insight in how you can analyze physical systems in such a way that you make accurate and correct assumptions and you are able to find the right answers. I hope to see you again.
Manorama Horizon. Learning made simple.